So welcome to the continuing videos for Math 1500 Calculus 1. So in the video on polynomials, we talked about the sum rule, the difference rule, and the constant multiple rule. But we also mentioned the fact that we can't take the derivative of two functions being multiplied by taking their derivatives and multiplying them. So because of that, we are left answering the question, well, how do we deal with products? How do we take the derivative of x times e to the x? How do we take the derivative of e to the x divided by x? If the perhaps most natural way of doing it doesn't turn out to work, what does work? And so that's what we're going to see in this section. First of all, we're going to develop the product rule. Quotient rule will be similar, as well as to see some examples of using it. So suppose we had some function h of x, which is equal to f of x times g of x. And we want to find the derivative of h of x. So the derivative of h of x, in fact, it's probably a bad idea to use the letter h for reasons that will become abundantly clear in just a minute. So the derivative of j of x is going to be the limit as h approaches 0 of j of x plus h minus j of x all divided by h. Definition of the derivative, nothing too crazy there. And then we just plug it into the function as we have before. So everything seems pretty normal, same as the addition, same as the subtraction, same as the constant multiple, same as power rule and all that kind of stuff. But the problem is we get stuck. We get stuck at this point because, unlike the sum rule or the difference rule, we can't separate the f's and the g's as easily as we saw before. Before, when it was addition, when we had these things being added, then we could separate the f of x plus h minus f of x divided by h. That would give us the derivative of f, and similarly we get the derivative of g. So in this case we can't, because if we want f of x plus h minus f of x, well, the f of x plus h is attached to this g of x plus h. And we can't factor out the g because it's a different g over here. Because of that, we're a little bit stuck. If this was g of x plus h, we wouldn't have a problem, or if this was g of x, we wouldn't have a problem. But they're not. So what are we going to do? So the idea is if we want this g of x to be g of x plus h, we're going to make that change. So we're going to take our f of x plus h times g of x plus h, and we're going to subtract an f of x plus h times g of x. Oops, that's not what we wanted. We're going to subtract an f of x times g of x plus h. Now, what we've done here is change the fraction, and we're not allowed to do that. We're not allowed to change g of x to g of x plus h. That changes the fraction. We don't want to do that. So what we need to do is we need to fix that up. So we're going to add in f of x times g of x plus h. So what we've done here is we've added and subtracted the exact same term in that numerator. Now that obviously doesn't change it. The harder question to understand is why we're doing this, and the reason why we're doing this is because now if we factor out the g of x plus h, we end up with our f of x plus h minus f of x over h thing that we saw with the sum rule, the difference rule, the constant multiple rule. That being said, if you subtract something, you have to add the same thing. And we'll notice down here that we have an f of x in both of these terms, in which case we can also factor that out. So with a little bit more algebra, we end up getting the limit as h approaches 0 of, well, that's g of x plus h times f of x plus h minus f of x all divided by h plus f of x times g of x plus h minus g of x all divided by h. So, assuming all these limits exist, then that means that this is going to be equal to the limit as h approaches 0 of g of x plus h minus the limit as h approaches 0 of f of x plus h minus f of x all divided by h. So right now we're just assuming all these limits exist. We'll talk about why they exist in just a minute. The limit as h approaches 0 of f of x and the limit as h approaches 0 of g of x plus h minus g of x all divided by h. So, assuming all these limits exist, we have this one right here. If g is a continuous function, then we can just plug in h equals 0 and we'll get g of x. If this limit exists, then it's equal to the f prime of x, in other words, if it's differentiable. In this case, f of x doesn't have an h, so it's just a constant, so that limit always exists. And this one here is just going to be g prime of x. So, in order for these two limits here and here to exist, we need the function to be differentiable. For this one to exist and equal g of x, we need it to be continuous. But we also know that if a function is differentiable, then it has to be continuous. So because of that, the only conditions we need is that f and g are differentiable. And that leads us to the following theorem. So if f and g are differentiable, then the derivative of f times g is equal to, now we're going to write this slightly different than the order than what we wrote it before. We'll talk about why in just a second. But this is f prime of x times g of x plus f of x times g prime of x. So, in other words, we're taking the derivatives of our functions each individually, but then multiplying it by the other function, not multiplying it by the other derivative. So f prime times g plus f times g prime. Now, we could have started right from the beginning with division and had something very similar. So this isn't obvious, but if we had done it as we did before, we could have made similar arguments and actually got what we'll call the quotient rule, which is f prime g but minus f times g prime over the denominator squared. All right, so when it comes to remembering the product rule, obviously it doesn't matter. You could switch these around. It's not going to affect the answer. You could have switched these around. It won't affect the answer. That's fine. However, we can also switch these two terms around. But I would strongly suggest that you write them in the order that we do, because if you switch these around in the quotient rule, our answer becomes wrong. It becomes negative of what the answer should be. And turning a positive derivative into a negative has huge bad implications later on. So you don't want to make that mistake. Typically, students who remember this in the opposite order, that won't make the product wrong, but those students also tend to remember this in the wrong order, and that's not such a good thing. So because of that, I would strongly recommend writing it in the order that we do. For those of you who are planning on taking some higher mathematics courses beyond just calculus, you might also want to remember it as f comes before g on each of these. It doesn't matter in this course at all, but in other courses, when you start talking about derivatives of functions where the order does matter, then all of a sudden it has to be in this order, like when you start talking about vectors and stuff like that. All right, anyway, so these are our product and quotient rules, so let's see some examples of using them. So let's compute the derivative of f prime of x if f of x are equal to these four functions. So you'll notice all of these functions are combinations of polynomials and the exponential e to the x, either multiplied or divided. So we're taking what we already know about polynomials and exponential functions and writing them in terms of multiplication and division. So in these examples, we'll write out every single step. In general, you may want to discuss with your instructor in terms of how much work they are expecting you to show. So in this case, the derivative of x times e to the x is going to be, using the product rule, the derivative of x times e to the x plus x times the derivative of e to the x. So this is how we use the product rule. Think of the little x and the e to the x as being the f and the g in our actual product rule. So this is the application of the product rule. The derivative of x is 1. The derivative of e to the x is e to the x. And so we get e to the x plus x times e to the x. Again, you'll want to talk to your instructor in terms of how much simplifying they want you to do, whether it's fine to leave it like this, whether they want you to leave it like that, or any other form for that matter. As for e to the x divided by x, that's just a straight up application of the quotient rule. So that's the derivative of the top times the bottom, plus the top times the derivative of the bottom, all over that denominator squared. So this is our application of the quotient rule. So that's x times e to the x. The derivative of e to the x is e to the x. Then we notice, oh, gotta be careful. Quotient rule is minus. So there's two main differences between the product rule and the quotient rule. The first obvious one is the denominator in the quotient rule. The second one is that the plus becomes a minus. And so this becomes minus 1 times e to the x all over the denominator squared. All right, so these are just the direct applications of using the quotient rule. For C, here we have to be a little bit careful because there's a step here that can often trip up students. So again, if we straight up use our definition or our quotient rule, not the definition, we get the derivative of 1 times x squared plus 1 minus 1 times the derivative of x squared plus 1. All over that denominator squared. The issue here is a lot of students, especially when they get comfortable, tend to jump right to the answer. Most of the time that's fine, and that's not necessarily wrong here. The issue becomes is what to do with this. It's the easiest part, but it's sometimes used in the wrong way. For example, when we are taking, let's say, e to the x plus 1, if we want to take that derivative, we know that that's equal to e to the x. Most of the time we don't put in the plus 0. We just leave it off. Again, for addition, that's not a big deal. But the classic mistake that happens here is people who will just leave it off and just write this as x squared plus 1 minus 1 times derivative of x squared plus 1, which is 2x, all divided by x squared. So this right here is a very common mistake. The derivative of 1, we're just not going to write it because the 0 doesn't matter or some other pile of garbage like that. That being said, yes, adding 0 doesn't make a difference, but multiplying by 0 certainly does. So the derivative of 1 is 0, meaning that our answer is negative 2x all over x squared plus 1 squared. But it's very common to have that term as part of the answer. It's wrong, but it's a very common thing because people think of the derivative of a constant as being nothing instead of the derivative of a constant as being 0. So make sure that when we're using this in conjunction with the product, but mostly the quotient rule, is that when you're taking the derivative of a constant in that numerator, that you're realizing that that 0 is multiplying by 0, and hence this entire first term goes away. All right. As for part D, so that's going to be our derivative of x squared plus x times e to the x all over our cubic polynomial. So again, we have a fraction. Because we have a fraction, this is a quotient rule. What makes this more complicated is that our numerator is more complicated. And that's the thing. The only way to really make a product rule or a quotient rule more complicated is to have a more complicated numerator or a more complicated denominator. Just using the product or quotient rule, once you do a couple examples, should be something that's really straightforward. That being said, the numerator and the denominator, those derivatives might be complicated too. And that's where the examples can sometimes snowball and get, quite long. Not necessarily hard, but long. Anyway, so we're going to use this as a quotient rule. So I would recommend not skipping this step. Again, the more comfortable you get, even if your teacher allows it, the more comfortable you get, the more steps you might feel apt to skip. But I definitely find in an example like this, where we have product rules inside quotient rules, that sometimes it's very easy to get a term mixed up. So it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. What makes this more complicated is the numerator. That derivative is its own product rule. So that's going to turn into the derivative of the numerator, which is of the first term here, which is 2x plus 1 times e to the x. This is a product rule, so it's a plus. X squared plus x times the derivative of e to the x, which is e to the x, all times that denominator. Minus the x squared plus x times e to the x times the derivative of the denominator, which is 3x squared. It's very common to forget the squared here. Do be careful with x cubed. And there we have our numerator all divided by our denominator squared. But trying to combine this and cram this into one step tends to be something that leads to little mistakes here and there. All right, so that's the product and quotient rule. Like I said, it really is difficult to make it more complicated in terms of an idea. The thing that can make them more complicated is just have more complicated numerators and denominators like we saw in this last example, part D. So that's it for this video, and we'll see you in the next one.